lecture number. Oh yeah, sorry, I forgot to give you the heads up to go record. Let me start over then. Hey everyone, welcome to lecture 3. Perfect, okay, great. All right, cool. All right, let me go ahead and do a screen share real quick. We'll look at the schedule and I'll check in with Arvind and Rohan to make sure we cover any announcements we need to get through, and then we'll get into today's lecture. Actually, before I do a screen share, yeah, Arvind and Rohan, I know we have a few issues to talk through after lecture and we'll get to those. Any other announcements that you guys would like to make before we hop into our lecture for today?
Just regarding the Python review session, as of now, we have received 28 votes on Piano. So once everybody votes, we can go ahead with the decision.
Okay, wonderful, great. And yeah, this is for a review session we like to do at the beginning of the year, especially for students who are new to Python. I'm sure Arvind already told you all this, but I think it's helpful. It's a helpful way just to get you a little bit more used to Python. And that will be a little bit more of an interactive session where I won't necessarily come with any agenda. I'll just be here to answer questions, and it can be a good way for you to get really used to image processing and using the Jupyter Notebook. So yeah, great. Any other announcements, guys?
Actually, we have a question from Austin, and there are a few more people who have said that the proposed timings does not work for them. So they asked if we could record the session and put it on Canvas.
Yeah, I don't see a reason we can't record the session, right? That should be fine, right?
Yeah, sounds good.
Yeah, no problem. So we'll make sure we get that recorded for you. No problem at all. And yes, there's, whenever you do stuff outside of class time, it's always a struggle. You're never going to be able to get something that works for everyone, unfortunately. So we'll do something that works for most people. And then, if you can't make it, we apologize. We will get that video up. And then you can always reach out to the TAs, of course. And then I'll have office hours starting next week as well. Great. Other announcements, Arvind and Rohan. Anything else going on we should discuss?
Maybe regarding the project proposals. So we are still working with the industrial partners. So maybe an announcement would be soon on Canvas regarding the industrial partners and a short description of what their project could be.
Right. Yep. Yeah. Thanks, Rohan and Arvind, for working on that. Rohan and Arvind have been working really hard to get in contact with all those partners, make sure that they are signed up for the year, and just get an idea of what the partner wants to work on. Some partners are going to be more open-ended. Some are going to have a very specific project they want to work on. And I think right now we have 6 confirmed. We might end up with 7 partners, something like that. So probably around half or a little less than half of groups will be working with an industry partner for this semester. All right, yeah, any other announcements, guys?
Nothing from my side.
Okay. All right, great. Well, welcome back, everybody. It's 12:34 or 2:34, so we can go ahead and hop into lecture. Arvind and Rohan, please feel free to hop in if there's anything that comes up, or if you remember any announcements that you might have missed or anything like that, please feel free to jump right in. We have screen recording going, which is great. I'll share my screen in a second here. I think those are all the things. I'm just happy that you guys can hear and see me. Let's make sure screen share works though before I jinx this. All right, so here's screen share. All right, cool. Okay, so I think that's coming through. We got the schedule here. So we have made it to 9:15. That's great. Here we are, lecture number 3. It's kind of like lecture 2. It's like our second big lecture. The first one, is mostly introductory stuff. So you had a little bit of homework to watch some videos. The last day to add drop classes was yesterday. Cool. All right, great. So let's get into it here. Let's hop right into some details. So last time we talked a bunch. Yeah, we talked a bunch about Roberts cross. So we left off last Thursday discussing Roberts cross. And just throw it in the chat window here for me if you don't mind. What was the purpose of Roberts cross, right? Why did Lawrence Roberts invent Roberts cross? He didn't call it Roberts cross at the time, I don't think, but what was he trying to do? Why did he invent this? Edge detection, exactly, right? Yep, finding edges. So as you can imagine, finding edges is possibly a useful thing to do, right? It's useful to find edges in images. And let me go ahead and pull up that Jupyter Notebook real quick here. I'm going to make this a little bit bigger as soon as this loads. There we go. Cool. And I just wanted to get to an animation real quick, or to a visualization. Let's see. Yeah, that's okay. This, yeah, there's Robert's cross. There we go. That's what we did last time. We coded this up in Python, learned the math, all that good stuff. So we did that, and we got these edges. And I left you off over the weekend to think about what are some of the problems with Robert's cross, right? So you can see that Robert's cross is helping us find edges, right? The edges are kind of glowing in our image here, which means that these have higher intensity values. So you could use these as part of some algorithm to helpfully identify bricks, for example. But what were some of the problems, right? We identified 4 specific issues with Robert's cross. So just throw it in the chat window. What do you remember from last time? What do you remember as an issue with Robert's cross? So I see Manessa says noise. Absolutely, yep. So Sai says no direction. Yep, exactly right. We don't get the direction of the edges. So Jeet says slant edges. Be more specific. What is the fancy science word for that? We say that Robert's cross is what? It's this word that starts with an A. If you want to sound smart, say this word. People will think you know what you're talking about. What is the problem with Robert's cross? Yeah, nice, good. A little spelling, very close. So Hernan, you said anisotropic, good. A-N-I-S, but yeah, anisotropic is the word, exactly. So anisotropic means that it doesn't respond equally in all directions. So a vertical edge will give you a stronger response than a slanted edge, which is not ideal, right? Perfect. And there was one more problem we identified, and this had to be, yeah, slow. Good. So Supreet says slow. Good. Yeah, great. So those are the problems, right? So today we're going to work on addressing those. Before we do that, we're going to zoom out a little bit though, and just talk about this general concept of image filtering. So if you remember, to implement Robert's cross, we had to write some code that basically did this. It took this little 2x2, we call it a kernel, and it slid it over the image. And it did a little bit of math for every window, basically, right? So that is an operation we had to do to make Robert's cross work. And it's actually such a common operation in computer vision that we're going to spend some time talking about it. So this operation is usually called filtering. It's related to an idea called convolution, which we'll get into, but we're going to call it filtering for now. And we're going to spend a while talking about it because it's such a common thing. So before we fully fix Robert's cross, we're going to zoom out a little bit and talk about image filtering in general. Okay, so let me hop to the next notebook. So the next notebook is called image filtering appropriately. There's a little reading if you want to do it here, and this is not required, but if you're curious, there's some additional reading you can do. And let me go ahead and hop into it here. So I want to hop into it. Here's those 4 problems with Robert's cross. So it's noisy, it's anisotropic, it's slow, and there's no direction. So let's tackle those one at a time. And to discuss filtering, I want to talk about the noise problem. I want to talk about how we would use image filtering to make our images less noisy. So let's get into it. So I'm first going to run this PyLab inline cell. So this imports NumPy and Matplotlib for me, which are 2 libraries that I use a lot in this course. And I'm going to load up an image. I'm going to load up this image of a ball. Notice that this is an image from your programming challenge. This is from the difficulty level medium 2. And the reason that this image is a little bit harder than some of the earlier or the easy images is because this image is especially noisy. So I took this image using the built-in webcam from my 2008 MacBook. So it's like a really old crappy webcam, right? And you can see, look how noisy that thing is, right? See all this grain in here and this kind of grossness, right? It's pretty disgusting. So that's kind of what's going to make this. We're going to use this image to demonstrate how to maybe remove some of that noise from an image. So let's get into that in a little bit. And something I wanted to show you again. So I really loved this idea from Lawrence Roberts, where he talked about, hey, one way to think about computer vision is to, instead of thinking about the this is the color, think about the pixel intensity value. Think about it as the height of a surface, right? So here I've taken this image, and the height of this surface that we're looking at in 3D here, the height corresponds to the pixel intensity value. So remember, in typical images, we use an unsigned 8-bit integer to represent the pixel intensity. And you can see that there's a really light spot here. So this light spot is going to have a value that's closer to white. It's going to be closer to 255. And you can see that that corresponds to like a hill or like a spike right here, right? And the darker regions, like see how this is so dark here, right? That's like a valley, right? So to do image processing is kind of just to do math on this landscape, on this like 3D landscape, which is kind of cool. It's a cool way to think about it. And it's also going to make it really clear that our images are noisy, right? So let's get into that a little bit more. So I'm going to go ahead and import a method from last time. So last time we wrote this convert to grayscale method. It's really simple. It's just a very simple one-line method. Feel free to go back to the last lecture to have a closer look at it. But I'm going to go ahead and import that. I'm going to convert my image to a grayscale image, and I'm going to normalize it between 0 and 1 by dividing by 255. Just one little fun Python comment. I can't help myself while we're here. Oops. I'd love to minimize that screen. Okay, it's back. Good. Okay, great. Cool. All right. Just real quick. Do you see this little period? So see this little period that I put right here, right? I don't think I actually have to do this right now, but I'm doing it as kind of a safety thing to make sure I don't do the wrong thing. Getting noise from my side. Okay, gotcha. Just got a comment that I'm getting a little noise. Disturbance in audio. Okay, let's see. I think it's my connection probably. Let me back this microphone off a little bit. Okay, so I move that back a little bit. Is that any better now? No, not any better? Okay. Is it like digital noise? Is the connection? Yeah, okay, the connection is breaking. Okay. So I may try to rejoin. I'm cutting off, okay. Gotcha. All right, so my options are to rejoin, or I could try a different microphone. I'd be surprised if it was this microphone though. Cutting off. How about now? Is it any better now? Testing, testing. How does this sound? Not any better. A lot of noise. Network noise. Okay. Let me try rejoining real quick, because if you can't hear me, it's going to be hard to learn anything. Maybe this is why some folks pre-record. All right. I will be right back. Audio's in. Perfect. Okay, cool. All right, I see an I guess. Okay, I see some betters. Okay, thank you guys for your patience. Please let me know if it goes out again, and we will do the same thing. So one of the many joys of remote lecturing. I will say though, even when you're in person in a lecture hall, there still can be technology problems. I've had my share of projector problems and adapter problems, so you really can't escape the technology problems. I think it's just part of being a human. Although we will, I think in 30 years or 40 years, we'll look back and laugh at how crappy our video conferencing software was. That's my prediction. Okay, so you guys can all hear me. Okay, perfect. Please let me know if my voice breaks up again, and we'll just do the same thing. Okay, so what I was about to show you was this dot. So I included this dot here, and I just want to talk about it for 1 second. Does anyone know, and I don't think, like I said, I don't think I have to do this. I don't think this dot is required, but sometimes I do it just to make sure that what I want to happen happens. So what is the reason, right? Why, throw it in the chat window, why do you think I've included a dot after this 255? Does anyone know what that's doing? Oh, screen share. Yes, that's pretty funny. Okay. All right, let's go back to here. Yep. So yeah, you guys have no idea what I'm looking at. All right, there we go. Okay. Arvind, is that what you were chatting me about, that I don't have my screen share going?
Yes, Professor.
About that. Thank you so much. All right. All right. Thanks for bearing with me, everybody. Okay, here we go. So yeah, so I see a few folks saying float, and let me show you. So if I just type 255 in Python, right? So it's the number 255. That's cool, no problem. If I do this, I do like, what is the type of this? I get int. So the type of this is int. If I want this to be a float, if I want to force this to be a float, I can do a couple things. So I can do .0, and now it's a float. And I can also, if I want to just take a little shortcut, you might see this in my code or other people's codes, I can also just do dot. Here, I want to make sure I'm dividing by a floating point number. I think in Python 2, this might have done something a little bit different, but this is Python 3, so it shouldn't really matter, I don't believe. But here, I'm just making sure that I'm dividing by a floating point because I want this to be cast to a float, basically. So just a tiny thing, just in case you noticed it. It's not a big deal, shouldn't impact your code, but I just wanted you to be aware of that this dot is not a typo. It's me making sure that my data type is float. Okay, so here's our image. And here is just a quick histogram of our image. There's our kind of spread of data. The darkest pixels are around 0.4, and the brightest ones are around close to 1, so pretty bright. And I'm going to pull in our Roberts cross. So last time we wrote a method called Roberts cross that actually does the Roberts cross operation. So I'll pull that in, and I'm going to run it, and I'll compute my edges. So here are my edges. And if you look carefully, there's kind of a lot of noise, right? And let me make this just a smidge bigger. Do like, oops, we do like this, so you can really see it. And we'll see it more in a second. But if you look at all this noise, right, all these little details, right? So what we're kind of hoping is that we can find a way to remove some of that noise. So start thinking a little bit, what could we do? What kind of math is going to make that noise go away? So that's what I want you to start thinking about. Now, just to show you in a little more detail, here's the three-dimensional version. This is that Roberts cross output visualized in 3D. And look at all those little bumps, right? So that's what we're kind of trying to avoid. So you do see kind of the nice regions of edge. You see these nice circular edge regions. You also see this big dark, this kind of spike right here. That looks kind of random, right? So if you look back at our image, that's kind of unfortunate. There it is right there again. What is that? So if you go back to here, that is actually a little knot on the wood. So the background is not, another reason this is the medium difficulty image. The background is not white, right? The background is wood in this case. So you get some noise, right? You get stuff like that. So, so that's our image. So what I'd like you to do now is to start thinking about what kind of math you can do to make this image less noisy. So hopefully you've had a chance to think about it. And I see a couple things in the chat window. I see Chandan said, apply a blur filter. So yeah, sure. Tell me this. And I see Gaussian blur from Christina. Cool. Okay, great. What would a blur, or so we're going to get to Gaussian in a minute. Gaussian's a great idea. We're going to end this notebook with Gaussian. Before we get to Gaussian though, can someone explain to me the intuition here? What kind of filter? Yeah, I see low pass filter, thresholding, reduced noise. For G, you said low pass filter, right? What makes a low pass filter? And I see Sean is kind of getting onto it now. Like, what makes it low pass? What makes this? What kind of math are we doing to make some of this noise go away? And I see Sean said mean filter, and that's really what I'm looking for. That's great. And low pass filter is correct too, and I'm just trying to get you to expand a little bit. So what we want to do is we want to take an average, because if you take an average of a little neighborhood, you should smooth out some of those wrinkles, some of that high frequency noise. So let's have a look. Let's get into that in more detail. So here's the idea. The idea is we take our input image that I'm calling X over here. We do some math, and we have this output image Y. And what we're doing here in this example is we're just taking the average of the local neighborhood. And the idea is that by doing that, if there's like a big spike here, for example, then by averaging it with the local neighborhood, you'll reduce the intensity of that spike. You'll kind of smooth things out. That's the idea. So let's get into it into some more detail here. And I guess the thing I want you to think about, is how does this operation change the appearance of your image? So start thinking about that a little bit. And let's get into it in more detail. And before I do it, though, I want to actually talk about how we implement this. So one way to think about this is that we are adding these 9 numbers together and dividing by 9. But kind of a more common way to think about this in computer vision is that we're operating on this little patch with a kernel like this. So these are the same operations, adding together and dividing by 9, as doing this, as multiplying by a kernel that's made up of 1/9. So we're going to think about filtering more in this way than we do in this way, but it's the same math. So hopefully that makes sense. So let me expand on this a little bit here. So this operation that I'm showing you here, we're taking this little patch of an image, and we're doing this mathematical operation with all 1/9, and I'm telling you that it's the same as adding them all together and dividing by 9. Does anyone know the name of this mathematical operation that we're doing here? That would be multiplying each, like you multiply 64 by 1/9, you multiply 48 by 1/9, you multiply 30 by 1/9, and you add all those results together and you get one number out. So yeah, what is this column? So I see, so Hernan says dot product, Minosa says convolution, Monica says dot product. Yeah, so the answer is dot product. So this is called a dot product. And we're going to use dot products all the time. So this is probably the first piece of linear algebra that we're going to reference here, is the idea of a dot product. And don't let dot products scare you. They're really easy. So all you do, you take 2 vectors or 2 matrices, you multiply it's called element-wise multiplication. So what I mean is that that 64 gets multiplied by that 1/9, and this 48 gets multiplied by that 1/9, and so on. So you multiply element-wise, and then you add all the results together. So we'll see that again and again. That's called a dot product. Okay, so let's go ahead and just look at how this is going to work. And there is a name. Let's see, what do I want you to take away from this? Yeah, so this operation has lots of different names. And I told you it's going to be called filtering. Here I'm going to give you a more specific name. So we're going to be doing cross correlation. It's going to be the most specific name for what we're about to do. So here is our input image. And I want to emphasize now that we could, our kernel could be made up of 1/9, for example, but it could be made up of anything, right? So in general, given any arbitrary image, we can filter that image, or we can perform cross correlation. And the mathematical symbol for cross correlation is this star, by taking this kernel and sliding it over each position in the image, and for each position computing a dot product, right? So that's the idea. And again, the dot product, the whole idea is you take each element and multiply it by the corresponding element in the kernel and add all the results together. Okay, so that's cross correlation. And I'm going to go ahead and let's get a poll ready, if you don't mind, Arvin and Rohan. I think we're almost ready for it here. I'll kind of introduce the problem. So here is the problem I want you to think about. Here's our first multiple choice problem of the day. And hopefully you can all see that text down here okay. I don't think I can make that too much bigger without hitting the edges. But here's the first question I want you to think about. So it's kind of related to our first question from last Thursday. So given an image I and a kernel K, and the image is of height H and width W, and the kernel is of size M by N, so it's M tall and N wide. If I filter an image, right, with this kernel, and again, I want you to assume that we don't go beyond the edges. There's no padding. So like I mentioned last time, we're going to take this kernel, we're going to slide it to the edge, and then we're going to stop, basically. Oh, my mouse is laggy. Okay, so we're going to stop this kernel at the edge. We won't go past the edges. So take a second and see if you can figure out what size the output image would be. So take 30 or 60 seconds, give this some thought, and we'll get a poll going. Okay. So hopefully you've had a chance to think through. Maybe take a few more seconds. I'll get my drawing ready that we'll use to discuss this in a second. And if you're stuck, it might be helpful to think about some example numbers, right? What could you plug in for H and W and M and N that could be helpful? Maybe just chat if you need a little more time. Otherwise, we'll finish. Okay, I don't see any chat. Okay. All right, let's give it a few more seconds, then we'll close. Okay, great. All right, let's go ahead and close it, Arvin and Rohan. Perfect, thanks so much. All right, so a lot of people saying D, great. All right, so D is the most popular answer. And then C is, oh, I guess there are 5 answers. So interesting. Does Zoom polling support 5 answers? It must, right? I only see 4 on my response area. Was there actually an E option on the poll?
Yes, Professor. It supports 5 options. We forgot to put an E option over there. We were not sure.
Oh, you forgot. Okay, no problem at all. Okay, no problem. I don't think E is the right answer, thankfully. So the one we left off is not the right answer, so that's good. So a lot of folks said D. So I believe D is the right answer. Let's get into it a little bit here. So I'll scroll down and let's kind of talk through the thinking on it. So before we get into this in too much detail, let's see, do I want to walk you through all this? No, I want to go ahead and go through the answer, yeah, before we go into that. Cool, okay, great. All right, so let me just walk you through my thinking just a little bit on this real quick. So let me switch my screen share, and I was doing a little bit of drawing during our talk or while you were thinking.
Professor?
Let me share this. Yes?
There is a bit of disturbance again.
Oh, disturbance in the audio again?
Yes.
Oh yeah, voice is breaking again. Yep, got it. Okay. All right. Well, I guess I'll just rejoin, right? That's all we can do. So give me a second. I'll be right back. Okay, so I made it back. Can you guys hear me? Okay, maybe not yet. Let's see. Okay. All right, how about that? Can you guys hear me? Oh, yeah, I'm seeing a lot of yeses. Great. Okay, thanks, guys. Okay, awesome, cool. All right, so thanks for your patience here. Let's go here. Cool. All right. Okay. So yes, now you can see my screen. Okay, great. So the example I wanted you to think through just briefly, let's pick numbers for the height and the width, right? And in this case, if my kernel was 3 by 3, for example, and I just picked these numbers just to help think through the problem, and my image was 5 by 5, for example, then here's one location my kernel could be in, right? And then if I keep going and I start sliding down, right, my kernel could also be, here. My next kernel could be here, and I kind of wanted to draw that. Let me do this. Okay, there we go. Cool. So my kernel could, I'm going to draw this like that. Cool. Okay. Where's your, okay. So my kernel could be here. Forgive the bad drawing. And then there's one more spot it could be basically. So here it could be here, it could be here, and then it might actually be helpful to do this on graph paper. It'd be a cool way to think about it too. So if this doesn't make sense, try it on graph paper. My 3 by 3 kernel could also be here. It could be here as well. Because if I was here, I would have 2 pixel spots and then 3, and then I'd get to the end. So my filtered image in this case, if I had a 5 by 5 image filtered by a 3 by 3, my resulting shape would be, there's 1, 2, 3 spots it can be in. So my resulting shape, I believe, would be 3 by 3, because it'd be the same in both directions. So what you can do then is you can think back to the problem and say, okay, if I plug in values of 5 for my height and width, and I plug in values of 3 for my kernel size, which answer gives me the right shape? So that's how I would solve the problem, is I would kind of try to reverse engineer it. And this kind of problem will be very similar to the problems you see on your quiz. So let me switch back to my notes. So that's what I'd recommend on a multiple choice question like that, is to try to plug in some numbers and see what works. And I think on D, if we plug in 5 minus 3 plus 1, we're going to get 3, and then same thing for here. So I think D is the only one that works. So that's the idea. And just in general, let's kind of look at this idea for a second. So what this says is that if I filter an image with a kernel of size m by n, right, the image is going to get smaller, which hopefully makes sense. And the larger your kernel, the smaller your image gets, because you can't go past the edges, basically. So, and the +1 is kind of an artifact of how we count. So that's the result. And again, we'll use this result in a minute in some actual code. So hopefully my audio and video works okay. So we've got through our first question. Hopefully that makes sense. If not, feel free to throw a question in Piazza. So let's get into a little more rigor here, and I want to kind of go a little further. Yeah, okay, because we're going to get into a little bit more math here. So we talked about some basic math, which was how do I figure out the size of my, output image. And now let's get into a little bit more mathematical description of cross correlation of filtering. So here's my image again, and I want to make sure we're really clear on the coordinate system. So I talked about the coordinate system a little bit last time, but in this course, we're going to follow the coordinate system that's used by Python and by Matplotlib when it visualizes images. And that coordinate system is that our first coordinate is I. It's kind of like X. It's our first coordinate, and it's down, positive down. And then our second coordinate is J, and it's positive right. And we discussed this a little bit last time, but hopefully this makes sense to you guys. When we sample images, right, we're indexing by that ith, the row, and then we're indexing by J, and that gives us the column. So I of 0, 0 is 3. I of 3, 1, I go down 3. So I go 0, 1, 2, 3, and then I go over 1, so it's 7. Just to make sure we're all on the same page here. What is I of, let's do I of 2, 1. So take a second. What is I of, oh, sorry, yeah, I of 2, 1. Take a second. Yeah, so I see a lot of 6s. Yep, good job. Yeah, a ton of 6s. Great job. Good, good, good. So 2, 1, so I go 0, 1, 2. So I'm on this row. And then 1 is my second index. So I go over 1, so I get to 6. Okay, so that's how we're going to be indexing. And that's about to be important because what I want you to do now basically is I want you to take a minute, and this will probably be some of the more serious math for this unit. Don't let it scare you though, it's not as bad as it looks, I promise. So I want you to think about how do we express this operation of cross correlation mathematically? What is the right mathematical description of this operation? And again, we're going to do intuition, we'll do mathematics, and we'll do code, right? So we'll do all three. But just real quick, let me scroll back up here to the animation. So this is the operation, right? So hopefully this operation makes sense intuitively. Like I want you to be able to explain this to someone and feel comfortable with what's happening with filtering. But kind of the next layer is, can you also explain this in the jargon of math, right? And math can be a little obfuscating sometimes, but it can also be really empowering. And if you're looking at the journal articles and things like that, then it's going to be important to have some knowledge of the math. So this is the operation. This is an animation that shows it, right? And now let's go ahead and hop into the mathematics, right? So here we go. So second question of the day, we'll open a poll in a minute. Not quite yet though, let's just discuss for a second. So before we open the poll, let me just discuss a few things with you to make sure you understand what's going on here. So we have an image I, a kernel K, and a filtered image S, and each of those are matrices. And these big sigmas, what do those do in mathematics? These big sigmas do? They take a sum, excellent, good. And the little number at the bottom tells you where to start. So this says start with n equals 0. And the big number at the top says stop at that value, in this case, capital N. And then finally, just notice that we're sampling, right? So we're sampling here. So this is saying take the sum across these values of n and take the sum across these values of m. And for each of these values, multiply the value of I at this index at I plus m comma j plus n times the value of k at m comma n. So this should start to feel a little bit like what we've discussed. Remember that to do cross correlation, the first thing you do is you take this kernel, right, and you put it kind of on top. You line it up right here in this spot, and you say, okay, what is 0 times 3? That's like the first piece of math you do, right? And you say, okay, 0 times 3 is 0. Great. Then you go down and you say, okay, what is 1 times -1? You say, okay, that's -1. Great. Then you keep going through all 9 locations. That gives you 9 numbers. You add those 9 numbers together and you should get 6. You should get that one number that results from that one spot. Then you move this kernel down to here and do the same thing. And there are 9 locations that this kernel can be. It can be here. It can be here, for example. There's 9 different locations it can be. So for each of those locations, you get a number. So that's the idea. So I'm going to go ahead and give you 30 or 60 seconds here. So let's go ahead and open up the poll, guys, please. Take a little bit of time, guys. And take 60 seconds or so, and we will discuss the answer.
Hello.
All right.
Yeah.
Okay, can you guys hear me? All right, so we got some votes in. That's great. And I see a lot of people have said C. Okay, let's kind of talk through it here real quick. Great. And let's, yeah, so Arvind and I have been chatting. Arvind and Rohan, please remind me when we get to, will you remind me when we have 5 minutes left, and we'll do a couple announcements at the end of class. Does that work for you?
Yes, sounds good, Professor.
Perfect, great. All right, cool. Okay, so let's go to my drawing here real quick. Okay, so hopefully my drawing, yep, there we go, cool, awesome, okay. So again, I would approach this problem probably using a process of elimination. I would probably look at the different answers and kind of plug in numbers and see what works. At a high level here, you know, one thing that I mentioned, or I didn't get a chance to really mention, is that this operation is applying to 1 pixel at a time. So like, this is telling you, how do I figure out like the I, jth position of image S, for example, right? So if I want to figure out the 0, 0 value, then this is the equation I solve to figure out that 1 value. And then I would use the same equation again if I want to plug in like, you know, 0, 1, for example, here. So let's kind of try to eliminate some answers or kind of think through what's going on here and try to help us zero in on the right answer. So first of all, this 2 summations, this throws off some people sometimes. Let's use the dimensions from the problem, right? So if m equals 3 and n equals 3, then this actually is going to be a sum up to 2. So from 0 to 2, so 0, 1, 2. And this is also going to be 2, right? 0, 1, 2. So if you think about this, this is kind of like an inner and an outer loop is what's going on. So this inner summation, right? This is saying take the value when n equals 0, when n equals 1, and when n equals 2 is what's really happening here. And let's look inside of here and see what's shifting around, right? So because we have this m and this n inside of this inside of the I, this is kind of shifting around the location that we sample in the image. So let's think about for a second. Let's decide. Let's let I equal 0, right? Let's let I equal 0, and let's let j equal 0. So that would correspond to us trying to compute the upper left corner. That's where I equals 0 and j equals 0, right? I should really actually, that's not a great idea. I should really say this. We're trying to compute this value. There we go. That's a little better. So if I equals 0 and j equals 0, we're trying to compute this value first, for example. And notice that we're sampling our kernel at m, n, for example, right? So when I equals, when m equals 0 and when n equals 0, we'll be sampling the 0, 0 position of our kernel, right? And we'll be sampling here, I is 0 and m is 0. So we'll again be sampling like the 0, 0 position. So what that corresponds to is taking this value, the 0, 0 position of our kernel, and multiplying it with the 0, 0 position of our image, which is actually exactly what we want to do. My audio is sucking again. Man, that's frustrating. Okay. Man, I made sure that I'm on an Ethernet connection and all this stuff, but you still can't always win with technology. Okay, is it really bad? Should I disconnect again? Or is it livable? I sound like Optimus Prime. Ah, okay, powerful, right. All right, I assume that you don't want your lecture from Optimus Prime, so I will rejoin. Give me 1 second, I'll be right back. Okay, so I should be back. Can you guys hear me? And do I sound like Optimus Prime? Yes. Yes, you can hear me, hopefully. No, you cannot hear me. No. All good, good. Okay.
Your audio is good, Professor.
Okay, great. Thank you, guys. All right, thanks for your patience. Okay. So we're back here, and hopefully while I was logged out for a second, got a chance to do a little more thinking. So what I'm trying to get at here is that by doing this, this gets us the right first value, which hopefully makes sense. And then you can keep iterating through and see which answer does what you want. So let me just look at D. Let's look at D together for a second. So on D, and I think D was the most popular answer, I think? Let's try to decide between D and C real quick. So on D, for example, I'm going to try to disprove D really fast. Ready? Here's what I'm going to do. So let's say we want to figure out, on D, let's let I equal 2, and let's let J equal 0. Just let's explore this test point for a second, right? So if I equals 2 and J equals 0, we're trying to find this value, right? We're saying, okay, let's compute this value because this is S of I comma J, so I is the row, so we go down 2, and then J is the first column, so it's the 0th column. Okay, so what this is telling us to do is to iterate again from 0 to 2 through and take a summation. And let's go ahead and go to the end for a second. So we know we're going to go all the way to 2, right? Let's kind of figure out the endpoint here. So the maximum value that n will hit. So n is going to reach a max value of 2. So let me do this real quick. Let's say we get to the m equals 2 point, and we get to the n equals 2 point, for example. We're about to have a problem. Does anyone see? It's a little small. Let me zoom in a little bit, maybe. That'll be helpful. Okay, oh, that's a little too far. There we go. We're about to have a problem. So if m equals 2 and I equals 2, right? And we do I plus m inside of here, right? 2 plus 2 is 4. What is a problem with this being 4? What kind of issue is that about to create? Any ideas? Why can't we put 4 in here? It's out of bounds, right? Exactly right. Good. So for that reason, I would eliminate D. It's because it has us reaching too far outside the kernel. The biggest value we ever want to have inside of here should be limited by the size of the kernel. So for that reason, I would delete D. Hopefully that makes sense. And then I do believe the answer is C, if I remember correctly. Let's just look at A for a second here. I think A is going to have, no, it won't have the same problem, but there's some problem with A. Oh yeah. Does anyone see the problem with A? There's a problem with A. What is the issue? So it's going to go too far, because if I plug in 3 here, because we know the size is 3, then I'm actually going to go too far again, because I'm going to go 0, 1, 2, 3, and there is no third or fourth basic row here, right? So this one's out for this reason. And then actually this is kind of interesting. So both of these are going to kind of work for you if you go through the math, but there's one subtle difference. So look carefully, and this is going to come up later in the course. So see this minus sign here, right? So what this minus sign does, it basically takes your kernel and it flips it, is what it does. So because we're kind of like going the other way. So if you want to explore that, walk through the math, but you don't have to know it in a lot of detail. But what it does is this operation here, this flips the kernel, both horizontally and vertically. If you do it, if you flip the kernel, then this operation is called convolution. This is called convolution, this operation. And remember, we're not doing convolution right now. What are we doing? What is it called? Close. It's not just correlation, though. It's cross correlation. Good. We're doing cross correlation. So the answer to this question is C. And we're doing cross correlation. Now, if you know anything about deep learning, you may have heard of convolutional neural networks. It turns out that under the hood, most neural networks actually do cross correlation. They don't do convolution, even though they're very similar operations. Just one has this kernel flipped, basically. But really, it shouldn't be called a convolutional neural network. Most of the time, it should be called a cross-correlational neural network, but nobody really wants to say that, so they call it a convolutional neural network. But really, the operation we're doing most of the time is cross-correlation. Okay, so hopefully that makes sense. That's a good thing to review. This will be just like a question you get on your quiz. If you have any doubts about this, please put them in Piazza, talk to a TA, talk to your classmates. But this is probably, I don't know, one of the most important pieces of math, probably besides gradient descent, that we'll discuss in this class. So let me switch back to my notes. Hopefully that all makes sense. And that is a summary, or that's kind of how I would think through that question. Okay, so I'm back on my notes. Great. So the answer to that one is C. Okay, and here's a little explanation to kind of talk you through it. So here is my implementation. So I promised to do concepts, math, and code. We've done the math, so let's do the code now. So here's my code. Again, this is very inefficient code. By the end of the year, we'll be doing code that's 1,000 times faster on the GPU. But for now, this is going to be fine. The main point of this code is to learn. So here's a method called filter2D. It takes in a grayscale image of size height by width. in a kernel of size m by n, just like our math. And it produces a filtered image back as the output. Now notice this here, right? So anybody, what am I doing in this line, right? And I'm going to clean up that spacing a little bit. So yeah, throw it in the chat window. What am I doing in this line here? Scaling the final image. Okay, close, close. We are, maybe scaling. Creating a matrix of 0. Yeah, right, exactly. We're making an empty matrix. And how did I figure out, where did this come from, right? Why is this the size? Excuse me. Yeah, it's the size of the result image. So remember, 20 minutes ago, I said, hey guys, if I filter an image with a kernel of size m by n, and I get back a result, excuse me, what size is it going to be? And a lot of you got it right. You said this answer, h minus n plus 1. And if you look down at our math, we're using exactly that answer, h minus n plus 1. So that's where that size comes from. Yeah, perfect, great. Okay, and here we're iterating through the rows, then the columns. And here we're doing one more little thing that I want to talk about for a second. You clear my throat there, hold on. All right, throat is clear, great. Okay, perfect. All right, so now let's think about this for a second real quick. So I told you that we're doing inside of our cross convolution. And I see a question, what does np.zeros imply? So np.zeros, it just means make a matrix, an empty matrix, that's full of zeros. I shouldn't say empty. Make a matrix full of zeros. Let me just show you a real quick. Great question about np.zeros. So if I do np.zeros, right, of 3, 3, for example. Oops. So I have to do a parentheses like this. That makes an empty matrix of size 3 by 3, for example. So it's just making this is basically a placeholder. So it's making an empty matrix that we can fill up with the answers, basically is what it's doing. Okay, so I'm iterating through here, but there's one thing I really want to talk about. Ready? So remember, I mentioned that, hey, we're going to be doing this one mathematical operation over and over and over, where we take, a grid and we multiply each value together and we add them all up. And what is that operation called again? One more time. What is that mathematical operation called? Dot product. Thank you. Thank you. Perfect. Good. It's called a dot product. Now here's where life gets a little confusing. Ready? So what do you think the NumPy, so we're using this library called NumPy to do our math. What do you think the NumPy notation is for dot product, right? So if you were just playing around, you might say, okay, it's np dot, and if I do a shift tab to do tab complete, or I can just tab to kind of do some tab complete here. Maybe there's like a dot product built in. And you might, this is another just Python tip, right? So if I start typing and I hit tab in the Jupyter Notebook, it will do autocomplete for me. And if I do this, right, there's this np.dot thing, right? And maybe this is dot product, right? Hopefully it is, right? Hopefully this is dot product. Ready? Let's try to find out. If I do question mark, let's see. So yeah, so this is the dot product of 2 arrays, but we're about to get in trouble. And I was hoping the docstring would actually help us. Let me show, I'm gonna have to show you a little bit more of an example. Let me show you real quick. So this is not gonna be exactly what we want. Let me show you why really fast. So let's do a simple example. So I think I can just do it like this. Let me do it like, well, let's just try that. Yeah, that's fine, okay. So this I think did what we expect. It's just the dot product of 2 vectors. So it did 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 9 plus 4 is 13, plus 1 is 14. So hopefully that makes sense. That's great. But now here's where we get into trouble. So most of the stuff we're going to be dealing with in this class are going to be matrices or tensors in higher dimensional space. So let me just make a quick little matrix for you real quick here. So let's take a matrix like that. So here is a 2 by 3 matrix. It has 2 rows and 3 columns. And let me show you where dot product is going to get us a little bit into trouble. Let me show you what I mean here exactly. So let me make this matrix called A. So here's this matrix called A. So here's A, cool, okay. And actually let's make this, well, no, this is fine for now. I was going to make it exactly like our problem, but let me make another matrix called B. Cool, here's B. Let's do the same thing. Okay. Actually, can I show this to you really dramatically? Maybe I can. Oh yeah, no, I definitely can. Okay, I have an idea. All right, bear with me. I want to show you exactly what's happening. So let me make this actually 3 by 3. I think this will make my point a little more clear, I think. So here are two matrices. So here's A, and here's a matrix B. Okay, so now finally we can do the dot product. Dot product is A, comma B, right? All right, cool. Okay. So what dimension are you hoping to get out? So when I press Shift Enter, what do you want? What dimension do you want? Do you want a matrix? You want a scalar? You want a vector? Okay, I see Monessa says 3 by 3. Okay. Now remember, we were hoping, what we hope for is that if we're really doing a dot product, right? If we're doing this dot product thing, we should just get out a scalar, right? Just one number, because it should take every little value, the 1 times the 3 and the 2 times the 2, and it should take the 3 times the 1 and add all those together and make one number, right? That's what we want, okay? But I don't think that's gonna happen. Let's try it, ready? Boom, okay. So we did not get out a scalar. We did not get out what we wanted, unfortunately. Does anyone know what NumPy did instead? What did it do instead of actually doing a dot product? It did matrix multiplication. That's the default. Yep, it's a matrix multiplication. Exactly right. Yep, which is a whole different thing, right? We'll be doing some matrix multiplication in our neural network module. This is another idea from linear algebra. This is a matrix product. Yep, so not a dot product. So it's called dot, but if you give it a matrix, it doesn't do dot, right? So confusingly, the thing we actually want to do is we want to do an np dot multiply. That does pointwise multiplication. So this will do 1 times 3 is 3. It'll do 2 times 2 is 4. It'll do 3 times 1 is 3. That gives us our pointwise. And then to make this into a dot product, right, I've done the pointwise multiplication. What am I missing? What's the last step I need to add to, yeah, I need to sum it, right? So I think, can I just do this? I'm not sure, let's find out. I can, yeah, so I can either just do a dot sum on the end, or if I want to get a little bit more verbose about it, I can do an np dot sum of that, and it'll give me the same thing. So because we have matrices, we had to, you know, kind of write our own dot product. So that shouldn't be too scary. Hopefully that makes sense. And I encourage you, if you're new to Python, and even if you're not, just play around a little bit, right? The Jupyter Notebook is a great place to experiment and just try stuff, right? That's what I do. I do that all the time at work. If I have a problem, I'll just open a notebook and I'll make sure I understand what's going on. So if you look here carefully, notice that for each little kernel, we are doing exactly this, right? We are doing a sum of a multiply. So that's how this filter2d method works. Just one other comment I'll make really fast right here, I'm sampling. We haven't discussed this in detail yet. Let's just talk about it for 1 second. This is the kind of thing we can cover in the review session more. But we've talked about this, like how I can take a of 0, 0, and that gives me the upper left corner. And we talked about the colon operator a little bit, but let's talk about it just a little bit more. What happens if I do that? So if I do 0, 2, what will that do instead of just sampling one value? What do you think? So I see some people saying 0 to 2. So Hill says 0 to 2. Dinesh says takes only 2. Only 2 what though? Monessa says first row. Okay. I believe what it's going to do is take the first 2 rows. Remember, we have rows first. I think to do, sometimes the indexing is confusing. Let's find out. I think what's going to happen is it's going to say 1, 1, I think. I don't think it's going to go all the way to the whole first column, but let's find out. I think you have to go to 3, I think, because it's not inclusive. But let's do this first. So yeah, so this has taken the first 2 rows from row 0 to 2. If I change this to 3, it'll take that whole first column. It'll do the first 3 rows. But this colon operator is a way to sample or take smaller matrices out of a big matrix, right? I could also do like this, for example. This will take the first 2 rows and the first 2 columns. So it's just indexing, slicing. Yep, perfect. Good. But if you haven't seen it before, it's a new thing. So I wanted to show you how that worked. And that's what I'm doing here. So I'm sampling the original image from I to I plus M. So I'm taking a little patch, basically. So that's how image filtering works. That's how I've written it in Python here. There's other ways to write it, but that's the idea. And let's go ahead and do it. All right, so let's go ahead and get into some filtering. So here's my kernel that we talked about earlier. It's made up of all 1/9. And we've done a bunch of talk about math and stuff. Let me just remind you that what we're trying to do in Python is we're trying to do this, right? We're trying to do these local averages. That's what we're trying to do. And we decided that we could use a little filter to do that. That was made up of 1/9. And now we've got all the math and all the code out of the way. We can finally do that. So let's do it. I think we're gonna do it here. So here's my kernel. These are values of 1/9, 0.11111, and I'm going to filter my image. So let's try it. So I'm gonna run filter 2D. I'm gonna pass in my grayscale image, and I'm gonna pass in my kernel. And the output is going to look, it's kind of slow, look how slow that is. Wow, all right. And the output is going to look like this. Here we go. Okay, so it looks kind of similar, but maybe you can see a little bit of a difference, and we'll do it more in a second. But you can see that hopefully some of this noise is a bit smoother. So it's been smooth. That was our goal this whole time. So we did a little bit of smoothing, right? But you can imagine you may want to smooth more, right? So using what we've discussed so far, take a second, right? How can we smooth this further, right? How could you make this even smoother than it is now using what we've done so far? Any ideas? So a Gaussian is a good idea, but the Gaussian actually won't make it much smoother. What else could we do? What else could we do to make this smoothing? Yeah, larger kernel. Good job, Nick. Yes, perfect. Cool. RIP Mike. Oh my gosh, we have like 5 minutes at a time. I'll be right back. Yes, I am muted. Okay, now you should hopefully be able to hear me. Okay, how many times do I get to rejoin this lecture? All right, cool. So you can hear me, you can see me, and then the last piece of screen sharing, we can get back to chatting. So a couple of you folks said the right thing. You said, hey, please make your kernel bigger. And you guys can hear me now, correct? Yes, perfect, great, okay. So you said make the kernel bigger. That's a great idea. If we take a larger average, we'll get a smoother image, is the idea. So let's have a look. So here what I'm gonna do is I'm gonna try a 9x9 kernel. So instead of doing a 3x3, here's a 9x9. And you can see when I run this code, it'll take just a second, you can see, hey, wow, that's really blurry, right? So we've smoothed it even further. So that's one way to make things smoother. So hopefully that makes sense. And let's try filtering a different image, and because I kind of want to talk about one more big concept as we're talking about smoothing and filtering. So here's another image, and let me make this a little bit bigger. Let me make this like 12 by 12 or something. So there it is. So here's an image of a brick that I smoothed the heck out of, right? And take a second, and maybe it's hard to see through the screen. Hopefully you can see it okay, but have a really careful look really closely at the edges especially. Is there anything weird? So I've smoothed this brick using a 9x9 kernel of all values of 1/81. I've done a local average. Excuse me. So yeah, I see pixelated edges. Yeah, so you see this kind of weird, like these little like hash marks, right? So it's kind of this artifact we're getting. So what I'm kind of getting at here is that what we're doing right now is called a boxcar function. So this just multiplying by a kernel that's all the same value. It's called a boxcar function. And it can result in this kind of noisiness. So a more common way to smooth your images is to use a Gaussian kernel, which we'll get into in a second. Ooh, but actually, yeah, I have a question for you first. So before we get into that, I want to kind of probe your understanding of filtering real quick. So let's kind of think through what's happening here. I want to make sure you understand why this is happening. So let's have a look at a fake image. So here's a toy image that I'm making. So here it is. I made it real quick. So I started with a matrix of zeros, and I put a 1 right in the center. So this is our image. It's zeros everywhere, and there's a 1 right here in the center, and it's of size 21 by 21. Okay. So what I want to think about is what happens when we filter, right? So here's the next poll of the day. So let's discuss it. So here's an image, and I want you to think for a second. what happens if I take this image and I filter it with this kernel? So this kernel is 1/25 everywhere. It's a 5 by 5, right? So take 30 seconds and let's discuss in 30 seconds or so what happens if we filter this image with that kernel. And respond to the poll once you have an answer. Okay, take about 10 or 15 more seconds, then we'll close the poll and we'll talk about the answer. And I guess we only have 12 minutes left. Man, it's a fast lecture. Let's see, maybe we'll take bets on if my audio is going to make it to, that's the next poll. Will my audio make it till the end of the, of the lecture? I think my vote is no. I hope it does, but we'll see. Okay, so let's go ahead and close that poll. Thank you. Perfect. All right, so the majority of folks said C. All right, cool. So most of you are wrong. Yeah, almost no one got it right. Good. I thought I could trick you. All right, good. Let's look at it. All right. So yes, let's have a look here. I think this was a challenge last year too. I don't know if you guys remember this, Rohan and Arvin, but I think a lot of folks missed this last year as well. So here's my drawing. Let's talk through this problem real quick. So here's my image in green, right? This green little square represents the one, the single one in the middle of the image. And remember that I'm sliding this kernel over, right? So this orange kernel is getting slid over the image. Now, first of all, when the kernel is off, right? So let's say when the kernel is like way up here, right? So it's not on that single one, right? What is going to be the output value here? Remember the green image is all zeros except for here, right? So what output value will I get when the kernel's here? 0, yeah. Good job, Monica. Yep, good job. Perfect. Good. So we get 0. Great. All right. Now, as soon as my kernel starts to touch this thing, let's say it just hits like right here, right? It just hits right here, okay? Remember, this kernel is made up of all 1/25s in all the spots. Every single spot is 1/25, right? What value am I going to get out when I have one single spot? What will I get out? I'll get 1/25, exactly, right? Because it's 0 everywhere. The background image is 0. The kernel is 1/25, but 1/25 times 0 is 0 everywhere except for here, where the background image is 1. Let me just underline that real quick. This is 1. The image is 1. So the output is just going to be 1 times 1/25, which is 1/25, right? Cool. And I think the intuition that I tricked a lot of you with was that you thought, okay, well, when the kernel gets like more centered over the image, right? So when the kernel gets here, surely it must have like a stronger value, right? When it's like dead center, right? But remember that there's only still 1 pixel that actually has a value of 1 inside the kernel. So what value will I get out? What's the value going to be here for this location? What do you guys think? Yeah, it's the same. It's 1 perfect. It's 1/25. Perfect. Good job. Okay. So it doesn't actually matter where it is. As long as it's over it, it's going to be 1/25. Cool. All right. And I see an interesting question, Supreet. Let me try to get to that in 1 second. Looks like a good question. Okay. So the answer then, it's not C and it's not D. And let me actually, I switched back to my other screen with my eyes, but not for you guys. Let me go back here. Cool. Okay. So for that reason, you know, it's not C and it's not D. It's got to be A or B. Okay. And I kind of wanted to make this, well, actually, I didn't make it too hard, I guess, right? So between A and B, look carefully, right? So the size should be 5 by 5, not 3 by 3. That's part of it. And the scale actually, so remember the value is always 1 out of 25. 1 out of 25 as a decimal is 0.04. So you could figure this out by looking at the value, or you could look at the size. But yeah, the answer is A. Yeah, exactly. Let me come back to your question, Supreet. Let's see. So you said, I understand using larger kernels makes it smoother and reduces noise, but doesn't that also make it harder to detect edges? Yeah, that's right. Yep. So it's kind of a balancing act, right? So we're going to get to that when we get to the Sobel operator. But you don't want to smooth too hard, right? Because if you smooth too much, you won't find edges. But if you don't smooth at all, you'll have too much noise. So it's kind of a balance. It's a really good question. Okay. So that's that question, and I'm going to stop in about 3 minutes to hand it over for a few announcements. But yeah, so Hernan says, how do you know when you found the sweet spot? Yeah, trial and error, right? So open up your Jupyter Notebook, play around with your parameters, see what you find. Let me show you a tool to help you though, actually. So there's more lecture here, but honestly, I think we're going to leave this part of the lecture alone for a little while. There's one more thing to know from this lecture, which is that instead of using this boxcar function, if we use a Gaussian kernel, we can get a little bit better smoothing. And I want to answer Hernan's question, or I want to give a little hint there real quick. So we're going to skip this part of the lecture for now, but there is one thing I want you to know. There's a method called make Gaussian kernel that you're welcome to use in your programming challenge. So I think we got a question. I think it was on Piazza. You are able to use my code in your programming challenges. You can use code from the notebooks. That's fine. Just don't use other people's code besides mine. But what I wanted to show you real quick is that we can blur our image using a Gaussian filter and get much nicer edges. So I wanted to show you that real quick. So do review the notebook so you can see that. But the one other thing I wanted to show you before we went to announcements real quick is just a nice little tool inside of Jupyter. So here it is. So there's this library called IPyWidgets, which are like little tools to help you with Jupyter. And there's this module called Interact. So I'm going to import that module here because I want to show you something. So I wrote this little method called blur and display, and it takes 2 parameters. It takes the size of a kernel, for example. And then when you do the Gaussian blurring, when you look over these nodes, there's also a parameter called sigma. Sigma controls how big and kind of wide your Gaussian is. Let me show you real quick. So here, hold on, it's coming. There we go. So different sigma values make your Gaussian bigger. So your kernel size, that's just the size of your grid down here, right? But you could still have a very small sigma, which would make your Gaussian spikier. So I can tune this parameter sigma, and that will make my filter, my Gaussian filter wider, basically. And I want to experiment with that to say, hey, you know, what's the right balance? Just like Hernan asked, he said, hey, how do I find the sweet spot? So what I would do in general is I would use this interact module, which I'm scrolling down to here. Give me 1 second. Here we go. Cool. Okay. No, that's not it actually. It's right here. Yep. So this interact module, I have 2 parameters. One is the kernel size, and one is that sigma value. And I take in those values, I make a Gaussian kernel, and then I filter the image, and then I display it. Right. So using this, it's pretty cool. I can just interactively, I can interact with my Jupyter Notebook, and I can play with these values. So watch. So you can see if I increase my kernel size, for example, it'll take a second to load here. It's a little slower than I would like, but if you have a fast function, it'll go a little bit faster. But you can see that as I change these values, the image gets blurrier and blurrier. Here's 11. There we go. Yeah, cool. So you can see it get blurrier and blurrier. So this interact module is kind of a nice way you can play with these sliders and see what different values generate. That's a nice way to find a sweet spot. But usually it's just experimental. Experimentation really is usually how these things get done. So like I said, we'll finish with a couple of announcements in just a couple of minutes. Before I close out lecture, hopefully this is helpful. Let me just give you a little hint of what's coming next time and give you some things to think about. So we talked about blurring, about filtering. Hopefully filtering makes sense. We're going to be doing a lot more filtering. In your programming challenge, if you do find problems with noise, you may try using Gaussian filtering. You can use this filter2d method. You can use this make Gaussian kernel method if you want. And this will help you reduce noise if you have noise problems when you work on your programming challenge. And then next time, and I was hoping we'd get to it today, but that's okay. We'll start strong next time. Next time, we're going to cover a little bit of a more sophisticated edge detector. This would help you with your programming challenge. So feel free to look at it before lecture next time. Let's see, do I have any reading for you? I want you to read, a little bit of history of the Huff transform. But that'll be for the next lecture, not for Thursday. But next time we'll talk about another edge detector called the Sobel edge detector, and we're going to implement it using filtering. And yeah, actually, it's fine. So I'd say don't worry about this too much. You could review it if you want to try to use it in your programming challenge. I think at the end, so we'll talk about how it works and all that good stuff next time. But at the end of the lecture on Thursday, I think I have a nice method for you, probably, like Sobel filter method. Just have a look at the notebook, and you may want to try using the Sobel method for filtering for your programming challenge. Okay, I think that's all I have to say. If you have any questions we end class, please throw them in the chat window. The one announcement we wanted to make sure that we discussed, and if you have a specific question, definitely throw it in there. The one announcement I wanted to make sure we discussed was about your programming, about your group projects. So for those, I just wanted to make sure everyone knew that for those projects, you're able to pick your own topics. So for your proposal, you know, we have a bunch of different kind of ideas to get you started thinking, and you can kind of use an existing idea if you want, but you are free to choose your own project. You're free to propose your own project topic, excuse me. And then after we get your proposal as part of this first deadline, then we will, then we might make some refinements just to make sure that you have a project that's reasonable. I'm gonna have a look at some of the questions real quick. Arvind and Rohan, anything else to add to the projects or any other announcements here?
So I wanted to add one thing. Just please explore different types of computer vision applications, and please go through the previous year projects, like what students have worked on, so that you can get a better idea of what you wanted to work on. That should help you for writing your project proposal.
Yeah, great. And I think Arvind has the same audio problem as me, maybe. I don't know whose is worse, but I was able to hear what you said, though, Arvind. Could you guys hear Arvind okay? He broke up a little bit, I think, but okay, good. You're perfect. Okay, great. So yeah, we see just a few last questions coming in. Perfect. Good, good, good. So I see a question, how to catch up for students who jumped into class yesterday. So yeah, if this is your first lecture, then start on Canvas. I would say just hop on Piazza and we'll give you a few links. So if it's your first class, hop on Piazza. You'll see the Piazza link in Canvas. Go on Piazza and just open up a post that you're new to class, and we'll provide the links and kind of get you going. Let's see, are proposals individual or do we need a group before? You can either submit individual proposals or you can submit group proposals. We recommend group, they don't have to be group. If we want to work with companies, how are we supposed to work on the proposal? Yeah, so we'll have a list of, we're waiting to hear back from certain companies about what they would like to work on. It's okay if you want to work for a certain company and you propose something and you end up changing a little bit. So just real quick, Rohan and Arvind, just so students have an idea. I know we put out feelers to some various companies, but we don't have answers from all of them yet, right? I think a couple have responded with topics. Is that we maybe have 2 or 3 topics in? Is that right?
Yes, we have 2 companies and we have 3 topics right now.
Okay, cool. Yeah. So for the other ones, and have we posted the names of the partners on Canvas yet? I don't think we have yet, right?
We haven't yet. I have a page ready for it, but haven't published it yet.
Yeah. Okay, maybe we go ahead and publish the names so students can, because some of the names will make it a little more obvious. And a lot of these questions you guys have about groups can be answered by reading the README. Let me show you where the README is real quick. So before you, the first place to look for any project-related question is going to be github.com/UNCCV. So here's all our course material. And then the course project is one of the repos under there. So the README has a lot of information that should help with your questions. And then if you have questions about timing, that again is going to be in the schedule. So if you're still confused, then ask on Piazza. Okay, great. Well, we're a little bit over time, so I'll let everyone go. Thanks for bearing with the audio issues today. Please post any further questions on Piazza, and we will get to them as soon as we can. All right, thanks, guys.
I think I'll just go ahead and post those names in the page on Piazza. What do you say, Arvind?
Uh, yeah.
Should I just go ahead and